So the next factor that favors Sn1 or Sn2 over the other one is solvent, the type of solvent. So the solvent can affect the rate of formation or stability of the charged species. Of course, the charged species here we are referring to Sn1, which forms carbocations. So the solvent can help the carbocation to be even more stable, even though probably the carbocation is tertiary, the solvent can even help to make it more stable. In general, there are two types of solvent. Both of them are going to be polar, but one class is protic solvent. So protic means that the structure of the solvent has a hydrogen bonded either to oxygen or nitrogen or fluorine. Okay, so in any molecule where you have H bonded to oxygen, hydrogen, fluorine, those solvents will be protic. For example, an example is water. You see how the hydrogens are bonded to oxygen, so this is protic. Obviously it's polar, but we are now saying it's protic. So ammonia will also expected to be protic because the hydrogens are bonded to nitrogen. Acetic acid is also protic because the oxygen is bonded to the hydrogen. So you see the trend. You see the trend of protic solvents. They have the hydrogens bonded to these electronegative elements, oxygen, nitrogen, oxygen. Okay, so those elements make the hydrogens acidic because they will be partially positive, and that's why they are protic. That's why these hydrogens are protic. They are partially positive. Okay, so protic solvents are good for dissolving anions, which obviously they are the leaving groups, but cations to a lesser degree. So they don't dissolve the cations as much. Okay, so this increases the rate of Sn1 but decreases Sn2 by, of course, dissolving the nucleophile, which will be negatively charged. So, for example, water, alcohols, acids, see an alcohol like methanol is protic. Those are protic solvents. So what we are saying here is for protic solvents, if you have a carbocation, okay, if you have a carbocation, the protic solvent which has these hydrogens bonded to the electronegative element will use the lone pairs to be attracted to the C+ center. This process is called solvation. And of course, we know the alkyl groups are donating electrons through bond. The alkyl groups are donating electrons through bond, right? So now the lone pairs of the solvents are donating electrons to the C+. So this is what the protic solvents do. They kind of solvate the carbocation. At the same time, the protic solvent will trap the leaving group. So let's say, actually it's not the nucleophile. Let's say Cl fell off out of a molecule like this. So let's say you had this and this fell off, and then you got the carbocation plus Cl minus. So the carbocation is going to be stabilized by, for example, the water molecule, the alcohol, or the acid, which is protic solvent. At the same time, this leaving group, we don't want it to go back and attack the carbocation. So what the solvent does, it hydrogen bonds to that leaving group. So, you know, the hydrogen is partially positive because oxygen pulls electrons towards itself. Oxygen will be partially negative. So the partially positive hydrogen will get attracted to the leaving group, which is the Cl, trapping the leaving group. So the leaving group will never go back to attack the carbocation. So protic solvents generally favor Sn1, but they will disfavor Sn2. How do they disfavor Sn2? Sn2 uses negatively charged nucleophiles. So if you use protic solvent, the nucleophile will be trapped. The nucleophile will never attack the partially positive carbon, right? Like, you know, this is supposed to attack this. Sorry, let's make this Br. The Cl is supposed to attack the carbon, then the Br should fall off. But if you have protic solvent, this Cl will be trapped in this manner by the protic solvent. Then the Cl will never play the role of a nucleophile. So that's how protic solvent disfavors Sn2, because it traps the nucleophile, but it favors Sn1 because after formation of carbocation you get a leaving group which you don't want to go back, so you use the solvent to trap it. Now the other type of solvents is polar aprotic solvents. Aprotic, A means there's no protic hydrogen, so you don't have hydrogens attached to either oxygen, nitrogen, or fluorine. So an example of those solvent, for example, is acetone, which is basically the nail polish remover. Okay, so this is acetone. You see, there's none of these hydrogens. None of this hydrogen is bonded to the oxygen, nitrogen, or fluorine. So all these hydrogens are not protic. So overall, the molecule becomes aprotic because we do not have a hydrogen directly bonded to oxygen, nitrogen, or fluorine, which would have qualified it as a protic solvent. So it's aprotic solvent because we don't have such hydrogens bonded to oxygen, nitrogen, or fluorine on this structure. DMSO is a relative to acetone. It's dimethyl sulfoxide. Where the carbon is in the middle, we put a sulfur. Okay, that's the structure of DMSO. Again, there's no hydrogens bonded to oxygen, nitrogen, or fluorine. DMF is an amide. It's dimethylformamide. So the nitrogen will have two CH3s. Again, you don't have any hydrogens directly bonded to oxygen, nitrogen, fluorine. Okay, so the structure of acetonitrile has a CH3 and a C triple bond N. Again, there's no hydrogen directly bonded to oxygen, nitrogen. So this is the common list for this class of aprotic solvents. This is the list for protic solvents: water, alcohols, and acids. So polar aprotic solvents will favor Sn2. Why? The reason being, these solvents will never trap the nucleophile like the protic solvent will trap the nucleophile, like in this case. They'll let the nucleophile be naked and free. So key point, polar aprotic solvents works with Sn2, favors Sn2. Polar protic solvents favors Sn1. So if you want one over the other, just use a different solvent in the reaction. Remember, the solvent is the medium where the reaction occurs. Okay, so we're looking at the effect of solvents polarity on Sn1. Now, you see, this is polar. These are protic solvents, obviously, because the hydrogens are directly bonded onto the oxygens. These are polar protic solvents. These numbers you're seeing here called dielectric constants. We usually use the symbol epsilon. The higher the number, the more polar the solvent, and that's what you want. So water has very high polarity based on its dielectric constant 78 compared to the rest. So this will be the best solvent for Sn1 out of all these solvents that will favor Sn1. Look at the relative rates. The rate is 150,000 times the rate if you use acetic acid. Okay, if you use acetic acid as a solvent, the rate will be 150,000 times lower as compared to using water for Sn1. Okay, for Sn2, we can compare the rates and compare also the dielectric constants. So you see how water is very polar. Look at the rate. in Sn2. And again, the problem with water, again, it's protic, polar and protic. So Sn2 usually uses negatively charged nucleophiles, which will be trapped again by the solvent. You don't want polar, you do not want polar protic solvents for Sn2. Okay. Even this one is a polar, this one is polar protic solvent. Polar protic solvent. Okay. Let me clean up the P. My stylus keeps on messing up. So the alcohol and the water are relatives. Both of them are polar and protic, and that disfavors Sn2. See, the rate is 1. But the moment you use these guys, which are polar but aprotic, that's a key word. Polar aprotic, look at the rates. The rates are in the thousands. Acetonitrile is the best, obviously, because it's of size. Okay, so these are the structures that I was just trying to draw on an earlier slide, which is here, structure of the polar aprotic solvent. So if I ask you which one will favor Sn1 or Sn2, you should be able to know just by looking at the structure. Remember that polar protic solvents will have hydrogens bonded onto oxygen, nitrogen, or fluorine in the structure. That's how you tell them. Okay. The other factor that favors one reaction over the other, comparing the two substitutions, is the strength of the nucleophile. Okay. Strength of the nucleophile. So Sn2 prefers negatively charged species, and I told you negatively charged species are stronger nucleophiles than their neutral derivatives, right? So stronger nucleophiles, Sn2. Weaker nucleophiles, Sn1. Remember, this is strong because of negative charge. This is weaker because it's neutral. Okay. So a nucleophile, a good nucleophile, should have a negative charge or high electron density. Now, the nucleophilic strength increases down a column of the periodic table. For example, if you are to compare Cl minus F minus Br minus of the group 7 elements, then this means that iodide is a better nucleophile than F. And remember, I said it's because of size. If it's big, then it has a chance to do what? Polarize. So the electrons will be on one side, and therefore you can attack a positive carbon center or a partially positive carbon center, because the electrons can be thrown on one side, and that causes polarization because the positive charges will be on the other side. Okay, so that's point number 2, all because of size. Okay, which goes with polarizability, which is what I've just explained here. You change the shape, and then the charges, like charges, will be on one end, and that's polarization. And now you can attack the electrophilic center. So nucleophilicity also increases from right to left of a row. So if you have CNOF, one would say that F should be a better F minus should be a better nucleophile than C minus. But it's not always the case. Some of the periods don't obey this rule number 3. The rule number 3 there is vague. I wouldn't vouch on it. The most important one is rule 1 and 2. Okay, so in summary, Sn1 versus Sn2. Will primary halide do Sn1? The answer is no. Why? Because you're gonna get a primary carbocations which is unstable. The most stable carbocation for this class, because there are more other stabler carbocations, if that's correct English, than tertiary. But for you guys, we know it's the tertiary. So the tertiary will want it. Secondary will also do Sn1, but not primary. Remember, for Sn1, It prefers tertiary over secondary, over primary, over metal, substrate, halide or carbocation. Now, Sn1 leads to formation of carbocation. Okay, it leads to formation of carbocation, which will be planar. So the nucleophile can attack from the right or from the left. So that's how you get racemization, where you'll have equal RNS product mixture. For Sn2, you just get an inversion. If you start with an R, you get an if you start with an S, you get an R product. If you start with an R reactant, you get an S product. Because the nucleophile attacks from the back, that's how you get inversion. Sn2 doesn't like tertiary substrates because of the back attack. The nucleophile will not have access to attack the carbon from the back. For example, here, it's crowded because of the metals, right? But Sn2 will readily happen with metal X. So the rate for Sn2 is metal X is preferred over primary, over secondary carbon, over tertiary alkyl halide like this guy. Okay? So primary will be something like this. Secondary will be something like that structure, because the carbon bearing the leaving group is bonded to two other carbons. Here the carbon bearing the Br leaving group is bonded to one other carbon, so it's primary, and this is just called metal halide. Next, nucleophile. I told you Sn1 prefers weak nucleophiles because the rate is not dependent on the concentration of the nucleophile. Remember what we said about the rate? Probably I should include it here. So the equation of the rate of Sn1 equals to K rate constant times the concentration of the electrophile, what others will call substrate. For Sn2, the rate will be equal to the concentration of the nucleophile and multiplied by K multiplied by the concentration of the electrophile. So you see, for Sn1, the nucleophile is not taking part, so it does not need to be, nucleophile does not need to be strong. If it's weak, it's fine. In fact, we like the weak ones to avoid mixtures. Now, the nucleophile for Sn2 is best when it's negatively charged. That's what we mean by anionic. Solvents, we just talked about solvents. So Sn1 would prefer protic solvents like H2O, alcohols, and carboxylic acids. Okay, those are just examples. And then for Sn2, you need polar aprotic solvents like acetone, dimethyl sulfoxide, or acetonitrile, or DMF, dimethylformamide. Okay, those ones are aprotic. None of the hydrogens bonded directly to oxygen, nitrogen, or fluorine. So that's the summary. Okay, again, to emphasize, primary substrates react Sn2. They cannot make stable carbocation. That's why Sn1 fails with primary substrate. Tertiary reacts with Sn1. The backside is too sterically crowded for Sn2, so tertiary fails Sn2. Secondary can react either with Sn1 or Sn2, because if you were to do the ranking Sn1 and Sn2, so Sn1 goes like this up to metal X, Sn2 will go like this. Okay, so you see, the secondary is right in the middle. If there's no stereochemistry, either method works. Of course, if there's no stereochemistry, then you don't expect racemization. But again, this would have been further into the topic that we'll not get into. This is survey organic. Okay, so now let's introduce elimination reactions. elimination reactions. So for substitution, we were replacing, let's say, a leaving group and doing the reaction and replacing it with a nucleophile. For elimination, you're making new pi bonds. Why is it called elimination? You have to remove what we call the beta hydrogen, and you have to lose a leaving group. Okay, so elimination reactions are different from substitutions. Okay, so in this case, where you are using things, species like as nucleophiles, this time you're gonna use those what you thought are nucleophiles as bases, because it's the bases that will be used to take out what we call the beta hydrogen. Okay, so the base is always used to accept the acidic hydrogen, which is, and to us is called the beta hydrogen. You get what we call a conjugate acid. Okay, again, what needed to be the nucleophile will be used to remove abstract a proton, and therefore in doing so it plays the role of a base, not a nucleophile. And in that case, you make a pi bond by elimination reaction. Now, it seems to be widely explained or vaguely explained. Let's look at a generic reaction. So let's say you have a nucleophile. So if you are to use a nucleophile and do substitution, what you'll have done is simply to attack this carbon and this should leave. That would have been the substitution. That would be the substitution route. You swap the leaving group with the nucleophile. But that's not what we're doing here. For eliminations, we will not do that. We'll not directly attack the carbon bearing the leaving group. For elimination, we will take out. This nucleophile will instead play the role of a base. So it's gonna take out this hydrogen, and then we use this bond to make a double bond, and now the leaving group can leave. That's one way we can do it. This process where it's concerted, it's called E2. Alternatively, the leaving group can leave, you get a plus charge, and then now we do this. That would have been E1. Okay? So bottom line, you're making a pi bond. Okay, that's the new pi bond. The leaving group leaves, and we will be concentrating on that, on elimination. The nucleophile, or the base that took out the hydrogen, makes the conjugate acid. Okay, when the base B takes out the hydrogen, get BH. If it were written as Nu minus, then you get NuH. So this elimination reaction is used to produce alkenes or alkynes from alkyl halides. For example, if you have this ethyl bromide and you add, let's say, a base like, you can still use OH minus. Instead of OH attacking this carbon, OH will be used as a base to take out the hydrogen next, sitting on the next door carbon, which we call the beta hydrogen. Okay, you take it out and then you make a double bond. So our product here would have been just a double bond, CH2, CH2, and of course Br minus, and of course the OH took out that hydrogen. The other product will be water. I put CH2 because I'm assuming you know there was CH3 here and there's CH2 here. E stands for elimination. So there are two types of eliminations. There's either E1, where you have to form a carbocation first, just like Sn1. So carbocation formed first. And then E2, where the reaction is concerted. You just push the arrows at once, no carbocation formation. So you realize that E2 and Sn2 don't have carbocation formation, so that's why they compete. E1 and E1 and Sn1 form carbocations, so that's why they compete. So you will have again to choose the best reagents that will favor E1 over Sn1, E2 over Sn2 because they share the same energy profile. So again, to remind you, okay, E2 is concerted. Why is it concerted? The alkyl halide and the base, they react at once. So no carbocation formation. So you just use other base, take out the hydrogen on sitting on a carbon bonded to the carbon bearing the leaving group, or the carbon next door, so to speak, make up double bond, and that leaves. You see, that's concerted. It happens at once. So the rate determining step will be dictated by the concentration of the alkyl halide, which is this, and the concentration of the base, because both of them are working together. Okay, so because these two species dictate the rate, then the reaction is bimolecular. But it's bimolecular elimination because you are making pi bonds. Because from this reaction, one would expect to get a new pi bond. So in this case, it will be CH2CH2 plus H2O plus Br minus, like I wrote before. Okay, so it's bimolecular, just like Sn2 is bimolecular. This is bimolecular. If you double the rate, if you double the concentration of alkyl halide, that means if you add more alkyl halide by doubling, the rate will double. If you double the concentration of the base, the rate will double. If you double both the concentration of the alkyl halide and the base, the rate will quadruple. Okay? Now, there is stereochemical requirement, which means that the hydrogen to be taken out, the hydrogen next door, okay, this hydrogen on this carbon, we call it a beta carbon, so the beta hydrogen to be removed must be 180 degrees in orientation to the leaving group. Okay, so that case is called anti-periplanar. So the hydrogen to be taken out and the leaving group must be 180 degrees apart, so that when you push the arrows, then the base, not the nucleophile, the base will take out the hydrogen, and then this bond will be used to make a double bond, and then this will fall off. That will be E2 because again the reaction is concerted. Both the base and the substrate or the alkyl halide are involved in this mechanism. So you're gonna end up with a conjugate acid, which in my case will be base and H, no longer nucleophiles, no substitution, and then you're gonna make a pi bond. Remember what we said a pi bond is. A pi bond is made by side-side overlap of two p orbitals. So that's what's happening here, up and below. So the product here will look like this, where this second bond is what you have up and below. The other byproduct will be the leaving group as it left. Okay, so now let's look at the E2 mechanism. So suppose I give you a base. So let me this time give you an alkoxide. So in fact, if you have methanol and you lose this hydrogen, you're gonna get OCH3. Because it's a methyl, we call this methoxide. Okay. If it were ethanol, this will be the structure of ethanol. If you lose this hydrogen, you get O minus CH3, CH2CH3. This one will be called ethoxide. Anyway, both methoxide and ethoxide belong to the class of chemicals called alkoxides because they are made of alkyl groups with oxygen. So alkoxides are strong bases. That's what I'm driving at. They are strong bases. So we can do E2. E2 wants strong bases. E1 weak bases. Sn1 wanted strong nucleophile. Sn1 wanted weak nucleophiles. Sn2 wanted strong nucleophiles. That's why Sn2 and E2 will compete, because whatever makes a strong base most likely is going to be a strong nucleophile which works with Sn2. Okay, so anyway, back to our mechanism. So I provided you with a typical strong base, and I'll ask you which hydrogen should I take out, A, B, or C. So the first thing you should realize is that the hydrogen to be taken out should be from a carbon next door to the carbon bearing the leaving group. We call this alpha carbon, we call this beta carbon, this should be beta 2. So we have to take the beta hydrogen. So we cannot take the hydrogen A because it's on the same carbon as the leaving group. We have to take either C or B. There are other hydrogens on the other side, but for purposes of teaching, let's just choose one that's going to be taken out. It's not A, could be B or C. Now out of B and C, which one is anti-periplanar? Remember the rule for E2? The hydrogen to be taken out must be anti-periplanar, which means 180 degrees apart in orientation to the leaving group. Our leaving group obviously is Br, because once it leaves, Br is electronegative, it stabilizes, the electronegativity stabilizes the leaving group to give you a weak base. We talked about that earlier on. So the base will choose to take out the hydrogen C, because you can see it's straight down, the leaving group is straight up. That qualifies anti-periplanar rule for E2. So take out that hydrogen, use this bond to make a double bond, and then the leaving group leaves. Okay, so you'll draw the product as this. So your chair is still there, but you made a double bond. The leaving group left. This hydrogen is still there. I can draw it here, and this hydrogen B is still there. I can draw it somewhere here at an angle. Okay. Okay, so that's the product for that example. Now what about here? Which one should we take out? So let's say you have another strong base, let's say OH minus. So this time you have the hydrogen, the beta hydrogen here. Okay, let me just call this A, B, and C. Which one will you take out? Which one? None of them for now, none of them. So what you'll have to do is a ring flip first. We talked about ring flips before. So let's draw the ring flip, and then we'll draw the product. So this is the ring flip. After flipping, carbon A will be tipped up. It still has the touch butyl group, and let's call ABC, then let's call this D. So C is right here, and then D, the bromine is equatorial down, so it's gonna go axial down. Alright, so this is a flipped ring, and now this gives you an idea, and it shows you that, okay, now that you have this structure where this is A, this is B, where is B? This is B, and then this is hydrogen C, yeah. So it shows you that you need to take out hydrogen B, because after the flip, now hydrogen B is 180 degrees to the leaving group. If you forgot about the flip, anything that's equatorial up like this one will end up axial up. Then the BR here is equatorial down, so it's gonna end up axial down. So the equatorial and axial are switched, but the up and down stay the same. So now you have the beta hydrogen and the leaving group 180 degrees apart, and that's anti-coplanar. Only then will the base come to take out the relevant hydrogen. So the base will come and pull out this hydrogen. You make a double bond, and then this leaves. Okay, so let me get rid of this other arrow so you can clearly see my mechanism. So the product will look like this. So you have the third butyl group and your chair with the double bond right there. So this will be the product. Okay, I've emphasized the anti-planar rule, 180 degrees orientation of the beta hydrogen relative to the leaving group. You have to know that. Okay, so what are the effects of structure on E2 mechanism? How does the structure of the alkyl halide affect E2 mechanism? Now, if you choose to use ethoxide, remember what I told you. Most of the time, negatively charged species are strong nucleophiles. But here we are thinking elimination, so we are taking this to be a base because elimination uses bases, not nucleophiles. So if you think that way, then one will want to take out a hydrogen that's anti-coplanar to this. So I think I'll have to redraw this 1, 2, 3, 4, 1, 2, 3, 4. I'll just have to redraw it somehow to favor my explanation here. So suppose we use this as a base and take out a hydrogen sitting on a neighboring carbon, what we call a beta carbon, beta hydrogen, and then use the bond to make a double bond. Okay, after taking out the hydrogen, and this falls off, you are gonna end up with this structure, which is basically what you have here flipped over. Now notice that this is primary alkyl halide. Can you see that? These are primary alkyl halide. The carbon bearing the leaving group is bonded to one other carbon, which is this carbon. So it's primary. So for primary alkyl halides, actually causes the Sn2 reaction to dominate over E2. Substitution will dominate over substitution dominate over elimination, because this will say, hey, the backside is not hindered anyway, so let me just do Sn2, and that's how you'll get this product, because this is the CH2 part and the CH3 part. So actually where I needed to cut to show you what attached is right here. Okay, so this is where the attachment was made. So this part came with the nucleophile. So the ethoxide, okay, this is called ethoxide, will either play the role of a nucleophile or a base. So if it plays the role of a base, you're gonna get this product. If it plays the role of a nucleophile following Sn2, you're gonna get this. After the leaving group leaves, Br- falls off in both cases. So this is Sn2 product, this is E2 product. What if you have a secondary alkyl halide? This is secondary again because the carbon bearing the leaving group is bonded to two other carbons. So again, we can use the ethoxide as a nucleophile, in which case you do a back attack because Sn2 can work on secondary substrates. Then you're gonna get this product right here. This is where you attached your O, CH2, CH3. Okay. All right. Alternatively, the ethoxide can choose to take out this hydrogen. So this is your ethoxide with a negative charge. Can use to take out this hydrogen, make a double bond as this leaves. You get what we call the E2 product here. That is less substituted. Actually, we'll call it mono substituted alkene. Alternatively, if the same substrate loses a beta hydrogen from this end, okay, so you take out this hydrogen, you make a double bond, and this falls off, then you're gonna get this elimination product. Anyway, what I want you to focus on is the percentages. So in this case, I say this is primary, the Sn2 will win because it's primary, E2 will lose. But now whenever it becomes more hindered, Sn2 doesn't like steric on the backside, then E2 will win. So both of these are from E2 reaction, elimination. Sn2 is only 18%. So the structure can dictate who wins, whether E2 or Sn2. So we are doing Sn2 versus E2. Who wins? Depends on the structure. If the structure is bulky, then E2 will be happy. If the structure is less bulky, like primary or methyl halide, then Sn2 will win. Okay. Effect of nucleophilicity, basicity of straightly hindered bases. Now, if you have such a nucleophile, I know it's negatively charged, but sulfur is very electronegative, so this piece is right here is not a strong base. It's a weak base, but it happens to be a strong nucleophile. This is one of the exceptions where it's not going to be strong nucleophile, strong base because of the negative charge. So only Sn2 will happen here because this is a weak base. E2 wants strong bases, not weak bases. So only Sn2 happens. You get the Sn2 product by itself, not E2. Now, if the base is bulky, then it's sterically hindered, then substitution will fail. Substitution will be disfavored. Sn2 disfavored because Sn2 doesn't like bulky substrates. So instead E2 will happen. So you will have to use this as a base to get the major product. And how I wish that this bromine was drawn down here to emphasize anti-periplanar rule. That's how you'll get this product right here. Okay, and then the base itself is gonna make its alcohol version after accepting the hydrogen, pulling out the beta hydrogen from the substrate. So it depends on the strength of the base and the nucleophilicity of the base, which might happen to be a nucleophile. Leaving group. Because E2 works with leaving groups, the better the leaving group, the faster the reaction. So obviously I minus is a better leaving group than Br minus because of size, which is better than Cr minus, which is better than F minus. I already said that if the size is big, then the leaving group is happy. Okay, so bigger size, happy leaving group. So E2, so if I ask you between this and this, which one will react faster in E2? The answer would be this, because it has an iodide which can fall off quicker than a Cl minus. That's what this slide is saying. We will continue from here to explain what we call Zaitsev rule.